Our next short video is going to take advantage of the Taylor series in a different way. We want to do something that's called Newton-Raphson Iteration. And this is the way that you find the root of a function. Or, it's a fancy way for saying the places where the function crosses zero. So here's a little test function. It's just got some wiggles in it. It's got two places where it crosses zero down there. And we want to use a Taylor series to find one of these zero crossings. Let's just do this schematically first. Suppose we take a guess and then try to improve it. That's why this is called an iteration, an iterative method. So suppose we guess right here. Now if we could find out what the tangent function was, right there, the linear function that's tangent to that, we could extend that all the way down to zero, and that would be a pretty good estimate of this root. Wouldn't work so well on this side. We would, if we did a tangent here, it would shoot way far away, and then we'd have to somehow work our way back. So the idea of the Newton-Raphson iteration is to take one tangent, make a guess, take a tangent at that location, figure out where that crosses zero, and then make a guess again from that location. And so in this case, we go back up to here, and then we get close and closer and closer and closer. Or if we did one over here, maybe the first guess would go to here, then we go up to there, then we shoot back here, then we go over there, and we ping pong back and forth and back and forth. And we might end up at this root, or we might end up at this root. We don't actually know which one we would get. The only thing we know is that if we guessed really close to that root, we would be likely to get there in a few guesses pretty quickly. Okay, so that's the schematic idea of how it works. We just take tangents repeatedly over and over again. Let's think about how we build that from the Taylor series. So our function f of x, what's the part of this that gives us the tangent? Well, it's not the quadratic. You can make a quadratic that just kind of kisses the function, but that wouldn't be a linear tangent function. That would be something that would have curvature in it. It would have second derivatives or dependence on the second power of x. So we're going to make a truncation of the Taylor series at just this n equals 1 term. So let's call that t. Oops, let me switch over to a different color. Let's call that t1, the truncation at the first term of x given a, which would just be f of a plus x minus a over 1 factorial, first derivative f of x, evaluated x equals a. Okay, so let's now think about what we want to choose for a and what we want to choose for x and what our goal is. Okay, suppose our first guess, let's call it guess number 1, x1, is this one. We're going to do the tangent near that. So let's write now the first order Taylor series of x1, which is equal to f of x1. Remember, this is a constant now, this is our first guess, plus x minus x1 over 1 factorial, which is just 1. We can stop writing that, but I'll write it now. The first derivative, df dx, evaluated at x equals x1. Okay, so that's our first derivative. This is the first guess that we have. And if this tangent function were to actually hit the line down here, that would mean that t1 of x given x1 would be equal to 0 for a particular x. That would be the x where this 0 is. So let's set this equal to 0 and solve for x. Okay? Now we have, here's the x hiding in here, here's an x1, here's an x1. So we have x minus x1 equals, first I would bring this over to the other side, minus f of x1, and then I would have divided by this, df of x dx evaluated at x equals x1. So I don't know what these derivatives are, but I surely could find them if you gave me this function. Okay, so I could then move the x1 to the other side and set the x equal to that. We can do that just by erasing. Okay. So this x1, we were hoping that's actually going to be the root, not the root of the real Taylor series, but the root of the linear approximation to the Taylor series. But here's where the iteration method comes in. We guessed x1 the first time around. We found something. We set it, the approximated Taylor series, to be equal to 0. That is, we followed the tangent all the way down to the root, and then we found a new x. This x, we're going to call x2, because that's going to be our second guess. Take the first guess here, then the second guess will be whatever x was the root of that original linear series. And then we plug it back in, and we repeat again. And we do that over and over again until we hopefully, well, we will either converge to one of these two roots. It's actually very difficult to tell which, but the closer you get to one, the more likely you are to end up at that one, broadly. Or we blow up, we go to infinity or something, because something could happen right here. If we happen to get really unlucky and hit something where this df dx was equal to 0, then we'd be in trouble. And now, through the magic of the fast erasure and redraw, here is the iterative method, written out simply. We make a guess for some x sub I. We evaluate that value minus the function evaluated there, divided by its derivative evaluated there. Shoot that all the way over to its root, the 0, which is going to occur at x of I plus 1. If that one's not close enough, we can check it by plugging in x of I plus 1 into f of x. If we don't think that's close enough to the root, then we increase I by 1, take x I plus 1 as the new x on this side, and we get an I plus 2. Do it again, I plus 3, etc. That's the iterative method, and it will converge on one of these points unless something terrible happens with this, which is possible, in which case you just restart with a different initial guess.